So in this problem, we're told we have 4 kilograms of certain gas contained within a piston cylinder assembly. The gas undergoes a polytropic process where P pressure times the volume raised to a constant is equal to a constant. So this kind of expression, PV raised to some constant equals a constant, is called a polytropic process. And in this case, the N is a 1.5. The initial pressure in the gas is 3 bars, absolute, and the initial volume is also given. The final volume is also given. Change in specific internal energy of the gas is also given here. We're told that there are no significant changes in kinetic or potential energies, and we're asked to find the net heat transfer for this process. So we're going to make the gas our system, and we'll apply the first law to that because what we're trying to do is find the heat transfer for the process. So we're trying to find the heat going into the system. That's what we're trying to find here. And of course there's going to be some work done by the system as the piston expands. So let's go ahead and write out the first law for that system. Change in total energy of the system is equal to the heat put into the system minus the work done by the system. We're of course trying to find the Q into the system. To find the change in total energy of the system, of course the change in total energy would be the change in the internal energy plus the change in kinetic energy plus the change in potential energy of the system. But we're told that we can neglect kinetic and potential energies for the gas. So that just leaves us the change in internal energy of the system, and that will just be the mass of the system times the change in the specific internal energy of the system. The reason I'm doing that is because we're told the change in specific internal energy of the system. The mass of the system is the 4 kilograms, so let me just make a note of that over here. So the mass of the system is 4 kilograms, that was given. Change in the internal energy of the system, specific internal energy, is minus 4.5 kilojoules per kilogram. So that's the change in the total energy of the system. Now to find the work done by the system, that work is the PDV work given here. So let's write that over on this side. The work done by the system will be PDV work. We go from some initial volume to some final volume. And now the pressure and volume relationship we're given right up here. It's this polytropic process. So I can rewrite that in the following way. So we're told P v to the 1.5 is equal to a constant. That constant, by the way, we can find from the initial conditions. We're told the initial pressure and the initial volume. So this would be the same as the initial pressure times the initial volume raised to the 1.5, where that initial pressure is 3 bars absolute, and the initial volume was 0.1 cubic meters. So if I rearrange that relationship, I'll get P is equal to P initial, V initial to the 1.5 divided by V to the 1.5. Okay, so I've just rearranged this expression in that. So I can plug that back in down here for the pressure. So we'll just substitute in. Now I need to evaluate that integral. Well, the P initial, V initial, those are just constants, so they'll come outside the integral. So let me do that. So I'll have V to the minus 1.5 times dV. Now this integral we can solve. That'll just be what we do is we add 1 into this and divide. So this is just kind of the standard way of evaluating that integral. So this will be minus 1.5 plus 1 times V to the minus 1.5 plus 1. That'd be evaluated at the final volume minus the initial volume, same sort of thing. So that's just that integral part. So this will just be minus 2 times V final to the minus 0.5 minus V initial to the minus 0.5. All right, so now we can plug in for our final volume. We're told the final volume up here is 0.2 cubic meters. The initial volume is given there. So we could evaluate this part. We can evaluate this part, and we can substitute that in up here. So it's getting a little bit messy here. So this will be plus 2 P initial, V initial 1.5 times V final to minus 0.5 minus V initial times the minus 0.5. Apologize for getting this all sort of crammed in there closely. But all I've done is just substituted in for the work by taking into account the minus sign there and the minus sign here. So this is our final expression that we can evaluate. We have all the terms that are all the numbers we need for that, so we can go ahead and plug them in, and we'll get the change in the, oops, I'm sorry, we're trying to solve for the heat transfer. So when you work out those numbers, the heat transfer is minus 0.426 kilojoules. So we had drawn the heat transfer going into the gas, but in fact, because there's a minus sign, there's actually heat or energy leaving the gas via heat transfer to the surroundings. Okay, so just to quickly recap, the way we approached this problem was applying the first law to the gas. The total change in total energy of the system is really just the change in the internal energy of the system, which is just the mass times the change in the specific internal energy. Define the work done by the gas. That is PDV work, and since it's a polytropic process, we can make use of this expression right over here or right here, where this constant is found from the initial conditions. Then the rest, this procedure here is just some basic math, and we substituted it all in to find the heat into the system, which in fact is leaving the system. Okay, we'll end it there.